Okay, and I know we still have a few more minutes until we hit 3 p.m., but I wanted to go ahead and get started. So I want to thank everyone for joining us in IGI Global's webinar, Sleptsov Net Computing, the solution to hypercomputations supporting cybersecurity and other applications, featuring Dr. Dmitry Zaitsev from the International Humanitarian University in Ukraine. While everyone gets settled in, I'd like to take the time to talk a little bit about IGI Global. So IGI Global is a leading international academic publisher for 30 years, with an ever-expanding portfolio of 4,000 reference books, over 175 highly indexed journals, and a broad collection of InfoSci databases. IGI Global is committed to providing the highest quality publications, excellent service, and has a steadfast pledge to the research community and underrepresented research. IGI Global publishes in 11 different subjects, including business and management, computer science and information technology, education, engineering, environmental, agricultural, and physical science, government and law, library and information science, media and communications, medical, healthcare and life sciences, security and forensics, and social sciences and humanities. Our presenters' research, along with thousands of other resources, are available in print and electronic format on IGI Global's online bookstore. Those who order directly from IGI Global through our online bookstore will receive a 20% discount on all purchases. I would also like to emphasize that today's webinar will be recorded, and all attendees will be sent a recording of the presentation after the webinar. Additionally, attendees will have an opportunity to participate in a live Q&A session with Dr. Zaitsev at the end of the presentation, and you can enter your questions using the chat feature located at the bottom of your GoToWebinar control panel. So feel free to type any questions in as we go, and we'll address them at the end of the presentation. And it is also my understanding that Dr. Sleptsov, the founder and creator of this actual software, will be joining us as well for the open Q&A session. So be sure to stay tuned to the end of the webinar for that. Okay, so now I'd like to go ahead and introduce our speaker. We have Dr. Zaitsev. So Dr. Zaitsev received his PhD degree in automated control from Kiev University of Cybernetics in Kiev, Ukraine in 1991. He also has a doctorate degree in telecommunications from Odessa National Academy of Telecommunications, Odessa in Ukraine, which he got in 2006. He is a ACM senior member, and he has published more than 100 papers, 2 books, and 2 chapters, including contributing to IGI Global's Encyclopedia of Information, Science, and Technology, 3rd and 4th editions. He has developed the universal Petri nets, the analysis of infinite Petri nets with regular structure, the decomposition of Petri nets and clans, and the method of synthesis of fuzzy logic and functions given by tables. Okay, so now I'm going to go ahead and hand it off to Dr. Zaitsev.
Thank you very much for your introduction, dear Caroline. And I'd like to add that recently I got absorbed in exascale computing and had improved my skill in this direction, and the best in the world team and the team of Jack Dangara to compare advantages of Petri net computing with traditional supercomputers, most powerful computers in the world. Well, Sleptsov net computing, and maybe a bit of strange first slide with its impression of rest and relaxation. And I was thinking about this expression mainly because we can see these palm trees growing highly into the sky, and we feel this feeling of rest and calm and quiet. So Sleptsov net computing gives us growth of performance. It gives us sky performance. And it allows programmers to have a bit of rest, a bit of relaxation, because programming in Sleptsov net is not so laborious as usual programming. And the basic question of this presentation could be represented rather simple in this strict black and white concept, and it may be put in a more solid way, in Hamlet-like way, to draw or not to draw. When we write very little, maybe a bigger program, but not so big, if small and medium program, we can do it directly. We can write it in a programming language, and we can enjoy our results. If we develop a big programming system, it starts working when you finished box of drawing. So you are drawing schemes, connections of data, connections of control. And in a book of John Fox from IBM, it was said about an airplane that it starts flying when the weight of documentation is greater than the weight of an airplane itself. So you should do much drawing, which is auxiliary. Why? Why you cannot draw programs simply? Well, let us study history of this question. When we think about place and transition nets, usually people say Petri nets after Carl Petri. And we started to study this question deeply, and we came to the process charts of family team, Frank and Lillian Gilbreth, who worked in United States, and they published their paper in 1921. More than 20 years after, it was adopted as a standard for operation and flow processes, and it was adopted to the programming for computers in this specification of Hermann Goldstein and John von Neumann. By the way, Holstein and von Neumann implemented only sequential part of the Frank and Lillian Gilbreth schemes. Well, let us cast a look on the original scheme of Lillian and Frank Gilbreth, and this scheme process chart specifies a production process. It contains different graphical blocks. It contains data and processes and provides synchronization of events. So we have different parallel branches, and we can even connect parts of scheme which are represented on the different pages. And different kinds of block provide special operations of connection for processes and data. I rather say that place transition nets, which appeared in 60s, represent a unification of Frank and Lillian Gilbreth schemata. And when we study the history of graphical programming, we find that for the first time it was developed to the full extent in Ukraine. The corresponding work had been started by Viktor Glushkov and continued by Igor Vilbitsky, and for more than 20 years, different systems which supported the process of drawing programs in so-called R scheme have been developed. They were developed for graphical screen of a computer and even for alphabetic digital terminals. It was possible to draw R schemes using usual lines with arrows and double lines to represent cycles. In this schemata, we have branching represented like a few lines which go through the same point, and with these double lines, loops are represented. Even now, you can download systems which provide writing programs using these R schemes. Recent times, UML is very popular, and UML is a graphical language to draw programs. It contains about a dozen of diagrams, and it combines graphical elements with textual specifications. But I rather say that it is good, very good, maybe too good system, because it contradicts main principle of programming, so-called keys principle. Too many diagrams and too complex to use it, to get acquainted with it. So maybe we need simpler concepts and maybe more homogeneous. Sometimes we find systems which use Petri net graph for programming, and we find a few dozens of such like systems. This slide contains a screenshot of one of them. Here we have places and transitions which are loaded as operators of some programming language. So usually Petri net schemata is combined with programming language because of Petri net weakness. The Petri net weakness consists in very slow representing of arithmetic operations. So when people think about parallel processes, concurrent processes, they use Petri net schemata. When they need arithmetic operations, they usually use some programming language. Otherwise, it will run very slow. And we offer a pure graphical programming where there is nothing save graphs. Inhibitor Sleptsov Net allows to implement such an approach because it is fast universal language of concurrent programming. It provides massively parallel computation with fine granulation on the level of separate addition and subtraction operations. And when implemented in computing memory, it have no usual disadvantages like processor memory bottlenecks for traditional architecture of computers and even for supercomputers, because we compute in memory. We need know these operations of data transmission between memory and processor. We do everything in parallel in special kind of computing memory. Now let us cast a look on the difference between Sleptsov Net and Petri net. Here we represent this difference on a very simple example. We have 5 tokens in the place P1 and 2 tokens in the place P2. So transition T1 is fireable, and by the way, if we estimate the multiplicity, its fireability condition, it equals 2. And in the Sleptsov net, we start this transition in 2 instances at step. And the next state is represented with this picture. In usual Petri net, we need 2 steps to represent this process because only one transition, only one instance of a transition fires at a step. Here we have multiplicity equal 2, but when we represent real-life computations, we can have great multiplicity and we obtain considerable speed up of computations. By the way, we studied this question and have proven mathematically and compared time complexity of operations for Petri nets and Sleptsov nets. On simple arithmetic operations, we have constant complexity versus linear complexity. And for multiplication and division operations, we have logarithmic complexity versus square complexity. Y by x is estimated as a square. In a general case, we obtain exponential speed up of computations when we compare Sleptsov nets with Petri nets. In the upper part of the slide, there is a strict mathematical specification of the variability condition of a Sleptsov net. For one arc, we have a variability condition which is estimated as division of the place marking by the multiplicity of an arc. And if we have an inhibitor arc, we estimate the variability condition as infinity. When we estimate variability conditions for a transition, we take minimum on all its input arcs. So we specified it mathematically, and now we start programming in Sleptsov net. So I'm going to pay some due attention to the peculiarity of programming in Sleptsov nets. When we write programs with Petri nets, we represent direct control flow from a start place to the final place. To start computations, we put here a token, and it is moving through the net, and maybe it allows firing of some other transitions which are connected to these places. This direct control flow can represent conveyor or pipeline processes as well, which corresponds to reenterable programs. If we need to restrict this control flow to have exactly one token in a place, we need to have this reverse inhibitor arcs. When we write programs in Sleptsov nets, we use reversed control flow. In the initial state, we have one token in each place, and we extract token from the start place to launch computations. And then this zero marking, I rather say a hole, is moving through the net, and it enables other transitions. Why we need this reverse control flow? Because as we considered on the previous slide, an inhibitor arc does not restrict the number of fireable conditions. So we use inhibitor arcs which are connected with the control flow places to control other transitions. And using the reversed control flow, we have no limitations. When we consider traditional operators of a programming language, how they are expressed with Sleptsov net. We take a sequence which is represented as a control flow in the previous slide, and here we can use subnets instead of transitions. We have branching, which corresponds to usual if-then-else operator. Here we have one branch, another branch, and they join in this place. We have a cycle. Here we represent a kind of while cycle, the body of the cycle, and then return to the beginning and the exit from this side. We can represent parallel execution as well. Here we have two parallel branches. which are represented recently with threads of a programming language or with special construct like par begin and par end. In addition to these standard kinds of control flow, we can drop an arbitrary control flow, which is represented with workflow nets. Workflow nets have been introduced by Professor Wil van der Aalst, and we modified them using reversed control flow. When we implement a program with operators, we need a definite set of elementary arithmetic, logic operations, and maybe some auxiliary copying operations. Here we represent them. Subnets to clean some variable, move value, copy value of a variable. Subnets which represents negation, disjunction and conjunction for usual binary logic, addition, subtraction and comparison operations. In our papers, we can find the representation for quick multiplication and addition, which uses more graphical elements. Let us consider some simple arithmetic operation, how it is implemented within a Sleptsov net. For instance, operation of addition. Here we have x, this place which represent the first term, and y which represent the second term, and the start place. When we extract the token from here, the net starts working. So when we extract a token, this transition is enabled, and it puts all the tokens into the final place Z, and transition T2 is enabled as well, and it can take tokens from the place Y at the same tact of time if we use maximal strategy. So finally, all the tokens are moved to the place, and here there is a sum of tokens. And when we have 3 zeros in these input places, they enable the transition T3, and it moves whole to the final place, which indicate that the computations have been completed. So when we think about implementation of this operation, we have a control flow here from S to F, and we have other transitions, so-called computing transitions and computing places, which represent some process of computations. When we think about general schemes, we have an operator, start and finish places, and we have variables, input variables and output variables of this operator. We introduce special abbreviation of dashed arcs, which represent connection of this copying subnets. When we have this dashed arc, it means that a copying subnet is attached, which copies value of this variable into the input place of an operator. And when the operator is finished, this subnet clean the value of output variable and moves value obtained by the operator. So using this abbreviation, we can provide more brief representation of our graphical programs. And here we explain how this construction, for instance, with addition operator, is expanded in a plain net. In the central part here we have addition subnet, and here we have two copying subnets which are attached in parallel to the start place. Finally, we attach cleaning subnet and moving subnet to move the value obtained during the computations. We can have brief constructions when we use the same variable as input and output, and here we reduced the size of this net, uh, removing some auxiliary operations. When we compose a Sleptsov Net program, we can use subnets, which correspond to routines of a usual programming language. And we can use an inline style when we insert entire subnet when it is indicated. And we can use call return style when we have only one copy of a subnet, and in each control flow we remember from which control flow this subnet has been called. Each approach has its advantages and maybe disadvantages, because this approach requires greater number of nodes, but it provides possibility to construct reenterable programs. And when we use call return style, we can reduce the number of graphical elements. Finally, to generalize the previous slides, we come to Sleptsov Net paradigm of computing. In the center of a Sleptsov Net computer, we have a processor of inhibitor Sleptsov nets, which is implemented in hardware as a computing memory. Plain inhibitor Sleptsov net is a kind of machine language for this computer, and the source program, which is written in a drawn as a loaded Sleptsov net, is compiled to a plain inhibitor Sleptsov net. Input and output data are represented as a marking of a given Sleptsov net, and we take output data from Sleptsov net places when the computations are finished. In this Sleptsov net computer scheme, we have this central element, and we can provide a mathematical concept as a prototype of a Sleptsov net processor when we try to specify a Sleptsov net processor by a Sleptsov net, which is common for computer science. We come to this concept of a universal Sleptsov net, which executes or runs a given Sleptsov net and its initial marking, and obtains its final marking with the net given Sleptsov net holds, and maybe it stored the transition firing sequence. There is an analogy to universal Turing machine, and by the way, there was a contest on a minimal universal Turing machine. Claude Shannon announced this contest in 1956, and there was a very exciting competition between Marvin Minsky and Watanabe, who construct the smallest net. Recently, a few years ago, two scientists from Ireland, Turlough Neary and Damien Woods, have constructed the smallest and fastest universal Petri nets. And still there is a question hanging either it is the minimal universal Turing machine or it can be reduced. Well, we have constructed more than a dozen of universal Petri and Sleptsov nets during about a decade, And our biggest universal nets contained thousands of graphical elements of nodes. Our best record was obtained a year ago, the universal Sleptsov net, which contains only 39 places and transitions, both to 39 vertices. Very interesting results have been obtained when we simulated the cellular automaton rule 110, which universality has been proven by Matthew Cook. Here we obtained the smallest block, which simulates a cell using 14 graphical elements, and when using synchronous Petri nets, we can reduce it to 3, one place and 2 transitions. I remind you that universal net is a prototype of a processor in this paradigm, in Sleptsov net paradigm of computing. Let us study how it is organized. I mean, universal Sleptsov net, the smallest one for the time being. On the central scheme of this net, we have a subnet TF, which represents transition function of a universal Turing machine of Neary and Woods, weakly universal Turing machine, which contains 2 states and uses 4 symbols. And we have HM subnet, which means head move. It simulates move of the control head. The content of the Turing machine tape is encoded using 3 places: X, the current symbol; L, the part of the working zone to the left of the current symbol; and R, the part of the working zone to the right of the current symbol. And we have left and right place, which represent the move of the control head either to the right or to the left. And we have 2 transitions which substitute the codes of the left and the right blank symbols in the weakly universal Turing machine. The place U represent the Turing machine state. This table contains the transition function of this universal Turing machine and its encoding. We use encoding of states starting from 0, 0 and 1, and we encode symbols starting from unit because we represent an empty word, code of an empty word as 0. So we start encoding from unit. And this slide contains the principles of the tape encoding. X, code of X goes directly to this place. And for the left and for the right parts of the working zone, we provide their codes, and we use a kind of encoding which corresponds to the to a number in a positional numbering system with the radix r. For our universal net, we choose the radix which equals 5, because we have 4 symbols plus 1 for this empty string or empty word. And here we represent the subnet which corresponds to the transition function. We were having 8 cells of this table, and we have 8 transitions which directly correspond to this table. We have code of the state and code of the current tape symbol, and the multiplicity of the arcs corresponds to the numbers in the transition table. So finally we obtain a new current symbol code and either left or right move. To start this net, we use direct control flow, and to start the subnet which implement the head moves, we use reverse control flow. The net, which simulates the Turing machine head move, it represents a combination. One subnet implements multiplication and addition, and it provides adding a symbol to some code, and another part implements division and modular operation to extract a symbol from code. In our previous universal net, there were distinct parts for each subnet. Here we merged them with the goal to reduce the number of graphical elements. So these two subnets are overlapped and condensed, and we obtained rather small number of graphical elements. When we combine these two subnets according to the central scheme, we obtain the final assembly of the universal Sleptsov net. Maybe it looks a bit tangled, but could you imagine that this net can run any given Sleptsov net? The Sleptsov net, a given Sleptsov net code is put to the place which represent the current symbol and the right and left parts of the Turing machine working zone. And at first we have proven mathematically that it is a universal Sleptsov net, and we double-checked it in simulators. We were using sequences of words for universal Turing machine, and we were simulating these computations on our universal Sleptsov net and obtained the complete correspondence of this sequence with the encoding of the corresponding words, which acknowledges that universal Sleptsov nets have been constructed. Now, when we can write programs with Sleptsov nets, when we know how they run on universal Sleptsov nets and maybe on computing memory, let us consider how we can write programs in Sleptsov nets for different application areas. The first application area is taken from the cybersecurity domain, and we implement a very known algorithm RSA, Rivas, Shamir, and Alderman, encryption decryption with open key. It uses the same formula both for encryption and decryption, and different power is taken either part of public key or part of private key. We represent this power bitwise and reduce it using multiplication, and construct corresponding Sleptsov net, which obtains reverse bitwise code. Implement this square operation like multiplication y by y, and it provides taking one next bit using this modular operation. Depending on the current bit, it either multiplies by x or omit this multiplication when the current bit equals 0. And then we compute modulo n from this formula. When implemented in hardware, it provides very fast encryption and decryption, and it opens prospect for the next security level, because recently RSA encryption decryption is implemented mainly for digital signature or key distributions. For other encryption decryption techniques with open key. That's like schemes of encryption decryption. With a Sleptsov Net chip, we can use this RSA encryption decryption for any transmitted packet. So it brings security of information exchange, local exchange or global exchange to the next security level. As a next example of programming with Sleptsov Net, we have chosen numerical methods, which play a central part in computer-aided design of different kind of objects, maybe aircraft, space shuttle, weather prediction, and so on. We illustrated it with Laplace equation, which is applied in thermodynamics and in other applications. And we use the following numerical scheme when we take values of 4 neighbors and divide them by 4. On the borders, we have some border conditions represented with constants L, U, R, and B. And each element, its value is taken divided by 4 using this arc. And then after division by 4, it is put to be summed in the places which represent values of its neighbors. In this example, we use a plane, two-dimensional example, and this lattice. And having a computing memory with big capacity, we can represent big lattices and compute the next state in one tact of Sleptsov network. And one tact equals some nanoseconds. So we can solve equations, differential equations, systems of differential equations, and the partial differential equations very fast, faster on the modern supercomputers. We take another domain, artificial intelligence. Recently, fuzzy logic is widely applied in fuzzy logic control to represent some maybe propositions in the area which require some degree of truth when we have a number in the range from 0 to 1, a real number which represent the truth value of a propositional variable. Here we use some discretization of this interval using constants from 0 to b, which is put at the weight as multiplicity on an arc here. And this net compute this fuzzy logic function. To compute it, it uses De Morgan law because we can represent conjunction, which is represented with minimum operation in fuzzy logic, and we can represent negation, which is implemented as subtraction. So it runs very fast and provides fast fuzzy control and the possibility for creating intellectual systems. Our other application area is taken from discrete time linear control, and we implemented lots of transfer functions in Sleptsov nets. Here we implement linear control according to the following system, standard system, where x is input variable, u is input variable, x is internal state, and y is an output variable. And our net multiplicity of arcs of this net correspond in this case to the matrix A, and they provide computations according to the equation in 2 tacts. So we obtain the required control only in 2 tacts, and 1 tact is equal to a few nanoseconds. So we have very fast control for very fast processes and very fast objects, such like some thermonuclear reactions, for instance, plasma, and for instance, some hypersonic flying objects. So implemented in hardware, it gives possibility for very fast control. When we cast a look on our today's presentation, we conclude that Sleptsov nets run exponentially faster than Petri nets. And universal Sleptsov net is a prototype of a processor. The smallest universal net contains about 40 nodes and runs in a polynomial time. Sleptsov net computing offers the following advantages: graphical concurrent language of programming, formal verification of concurrent programs, fine granulation of parallel processes to the level of addition, subtraction, multiplication, division by constant, which provides massively parallel computations. One aspect of these advantages, formal verification, is left beyond the scope of our presentation, but it is very significant because we verify our program, our concurrent program from the very beginning, from its first model. And we can provide formal verification for our final program, which is very significant for critical applications to have formally verified program. So it is an advantage, and you can find a more detailed description of this advantage in our papers. By the way, more than a dozen of papers have been published in respected journals. You can find a list, maybe reduced list of them on this slide. And a chapter has been published by IGI Global the previous year, a chapter in the Encyclopedia of Computer Technology, which represents a kind of complete overview of Sleptsov net programming. And if you started to like this approach, if you started to like Sleptsov net computing, please support Sleptsov net stack on Twitter and Facebook. And if you have questions, please feel free to write them directly to my email address, and maybe find some details, a list of papers on my website. Thank you very much for your attention.
Okay, thank you very much, Dr. Zaitsev. So at this time, we're going to go ahead and open it up for the live Q&A session. So if anyone has any questions on Dr. Zaitsev's presentation, if you could please enter them using the chat feature at the bottom of your GoTo control panel for us. And then we will go ahead and start going through them. I see we do have a few questions that did come in during the presentation. One thing I did want to mention, I know we talked about Dr. Sleptsov actually being a part of this presentation, but unfortunately he was unable to attend. However, he did send me an email and he wanted me to preface, quote, "I want to say that we now understood that IGI Global is a great master, promoter, and patron for disseminating new, innovative knowledge for all mankind. And I want to thank IGI Global for the sure implementation of the mission that you have proclaimed. Thank you very much. We wish you prosperity." And that is from, end quote, and that is from Dr. Sleptsov himself. So we thank you very much, Dr. Sleptsov, for this kind words, and we are very happy that we have an opportunity to disseminate your research as well as Dr. Zaitsev's research. So I'm going to go ahead and move into the Q&A portion of it. So once again, if you have any questions, go ahead and enter them into the chat box at the bottom of your GoToControl webinar panel. The first question we have for you, Dr. Zaitsev, is, could these nets apply in supply chain management or operations management? Can you please explain?
Well, Sleptsov nets can be applied successfully in the operation management. And by the way, it was the our first work and a part of my PhD work, which supervisor was Anatoly Sleptsov. And we've constructed a system for production control, which is named Opera Topaz. And it was working for, I think, some 10 years at Topaz plant in Ukraine. And if you are interested in this kind of application, you can upload this system from my website. It was implemented in 90s, so it works in MS-DOS, but it is very small and very fast. Recently, when people asked me to present it, I uploaded VirtualBox, installed MS-DOS and the Kirus driver, and it works perfectly well. So if required, we can rewrite this system, for instance, for Linux, X window, or other environment, and provide some remake of this system.
Okay, thank you very much. And I know this might actually kind of overlap with the previous question. You might have already answered it, but I know we've had a lot of questions regarding how Sleptsov Net can be applied to cybersecurity. So if you could go in and just explain a little bit more about that and the supercomputer model that you have talked about.
Well, thank you for this maybe very significant question, because people discuss very much on the pages of respected journals quantum computing. And we are waiting when it appears. But maybe today's level of technology does not give us possibility to hope that it will be maybe in a decade. And Sleptsov nets can run implemented in hardware using the current level of technology, because computing memory is very close to PLM, programmable logical matrices, which were applied for decades. So we can implement them, I say, in some half a year, in a year, and obtain very fast chips which provide encryption and decryption some 100 times faster than usual chips for these purposes. It will provide more security level, next security level, because it will allow us to use more sophisticated and more reliable algorithms. For instance, RSA, elliptic curve algorithms can be implemented as well. So it brings us a breakthrough in the security of our systems. It will allow us to defend them better using today's technology. It is maybe the main advantage of Sleptsov Net, because it does not require something extra. It requires only maybe some support for its implementation. That's all, and we will come to the next level of security.
Okay, thank you very much. And also, for those still listening, we did do an IGI Global Newsroom article with Dr. Sleptsov and Dr. Zaitsev, and I'm just going to briefly go through a few of the questions that were at the bottom of that follow-up article. I know previously it's been a discussion about all the controversy behind Sleptsov Net and Petri Net. Could you please explain a little bit more about that for us, Dr. Zaitsev?
Well, I was absorbed in this question for years because in literature of different countries, different titles were presented, because in USA literature, people were talking about vector addition systems after Karp and Miller. And in Europe, people were talking about Petri nets after Carl Petri, who introduced them in 1962 in his PhD. But when we studied this question deeply, we came to this family team of Gilbreth, who introduced very similar nets, maybe richer nets in 1921. And we can consider Petri nets as a unification of this Gilbreth flow charts for production processes. And when we compare Sleptsov net and Petri net, they use the same graphical notation, but the semantic of the transition firing is different. And in between of these two names, I could insert name of some Polish researcher, Andrew Salvitsky, who introduced maximal parallelism concept. It is in the middle. So in a Sleptsov net, we fire only one instance of a transition at a step, and the corresponding net is not a computationally universal system. When we apply Salvitsky concept, we can start a few transitions at a step, maximal number of transitions, but each transition is started in one instance. And we obtain computationally universal system, but it is running slow. So it possesses the same disadvantage of a Petri net, because it is running slower, exponentially slower than a Turing machine. And only a little amendment introduced by Anatoly Sleptsov allows a net to run fast. When, for instance, in a production, we have, for instance, two tools ready to implement some operation, we can start this operation in two copies, one on one tool and another on the another tool. And the same in a Sleptsov net. When we have multiple firing conditions, we start a transition in a number of copies, in the maximal number of copies. Because of this, we obtain a breakthrough in performance. So Petri nets were useful for years for parallel concurrent program schemata, but programming in Petri nets was hampered by the fact of their slow execution. And bringing this multiple start of transitions make them fast and provides possibility for their real-life implementation as a fast programming language and a fast supercomputer.
Okay, thank you very much for that explanation. It looks like we are running out of time, so I'm going to go ahead and close the open Q&A session. But like Dr. Zaitsev said, his contact information is available, and also my contact information is available at the end of the presentation. So if anyone has any additional questions, please feel free to reach out to us with any additional questions. So those who are interested in more information on this topic, be sure to check out Dr. Zaitsev's article, Sleptsov Net Computing and IGA Global's Encyclopedia of Information Science Technology, 4th edition. To tell you a little bit about this publication, the Encyclopedia of Information Science and Technology, 4th edition is a 10-volume set, which includes 705 original and previously unpublished research articles covering a full range of perspectives, applications, and techniques, all encompassing information science technology. So it blends seamlessly into this presentation. It has critical perspectives on the impact of information science and management and new technologies in modern settings, including but not limited to computer science, education, healthcare, government, engineering, business, natural, and physical sciences. So we are actually doing a special offer currently on this publication. So when your library invests in the electronic version of this, they will receive the 1st, 2nd, and 3rd editions with the purchase of the 4th edition ebook. Plus, we'll be able to take an additional 20% off when purchasing directly through IGI Global's online bookstore. So be sure your library knows about this information and recommend this comprehensive publication to your library today. Additionally, for more information, please check out the related publications on this topic, including publications that focus on statistical data, model-based design for effective control and systems development, agile software development, and then modern software engineering. All of IGI Global's publications and research are available as a part of IGI Global's InfoSci database collection, which includes InfoSci books, a collection of 3,900 books containing over 86,000 chapters, InfoSci journals, a collection of 175 journals with over 22,000 articles with 1 million citation references. We also offer specialized subject and discipline focused databases as well. Recently, we actually unveiled completely new pricing for our databases. And as a part of this new pricing, IGI Global is offering with InfoSci journals that for those who invest in InfoSci journals institutions, all of the IGI Global's hybrid open access fees will be waived for the journals. So all institutions who invest in this database will have, their researchers will have their IGI Global access fees waived. And this is just to provide an affordable way for academics to publish their research open access. And I did want to note that the research must be vetted and accepted into an IGI Global journal before the fees are waived. So definitely be sure to recommend these databases to your librarian and take advantage of that open access offer. I would again like to thank everyone for their time and for joining us today. And those who are interested in learning more about IGI Global, please be sure to visit our website, www.igi-global.com, and also be sure to visit our Publish With page. We're constantly looking for new book proposals, journal submissions and contents. We have our call for papers, call for chapters up there, and we're constantly looking for new projects in our 11 subjects. And that also includes computer science and information technology, cybersecurity and forensics, and engineering. So thank you once again, and our presentation has been recorded and will be sent to all attendees. So be sure to check your inboxes. I hope you will join us for upcoming webinars. And for any questions, please feel free to contact me at communications@igiglobal.com. So thank you very much, and I hope you all have a wonderful day.
Thank you. And I rather say that there was a great team to implement Sleptsov Net computing today. I especially glad that Dr. Pruber from London has attended this webinar because he is very known in the world, expert in cybersecurity. And thank you very much to all of you who attended this webinar. And I invite you to work together on the implementation of Sleptsov Net computing.